Hi, welcome. We're talking about Chapter 9, Section 2 on the circle and ellipse today in Precalculus. So let's just dive right in. We see right here, we see the equation of a circle. Should be some review from earlier in the year and first semester when we were transforming them. But the equation for a circle, to summarize real quick, is the quantity x minus h squared plus the quantity y minus k squared is equal to our radius squared, where r represents our radius, and h and k both represent the x and y coordinates of the center of our circle, respectively. And just some quick review on the definition of a circle. It is the set of all points that are equidistant from a fixed point, the center. Okay, so we're going to dive right in and do an example real quick. We notice right away that we have both an x squared term and a y squared term, okay, with a horizontal and vertical stretch that is exactly the same. So we know right away it's going to be a circle. Our figure is being stretched the exact same horizontally as it is vertically. So what we're going to have to do in order to make this equation look like this equation, which notice has two perfect square trinomials, is we're going to have to complete the square. So we're going to start by rewriting our equation such that we can complete the square, recalling that our additive identity is 0. So technically all we're going to be doing is adding 0. Now, quick review on completing the square. The mini equation to complete the square is quantity b over 2 squared. So we're going to take our quantity b, negative 6, divided by 2 is negative 3, squared is 9, so we're going to add 9 and subtract 9. We're going to take our quantity 4, divided by 2 is 2, squared is 4, and add 0 again. What that allows us to do is now factor a perfect square trinomial twice, and our equation starts looking more like the equation for a circle. Now this minus 9 and minus 7 together makes negative 16. We're just going to add that to the other side of the equation. And you see that now we have an equation that looks very similar to our equation for a circle, where we can identify our horizontal shift as being right 3 and our vertical shift as being down 2. With a radius, recall that 16 is equal to r squared, so r is equal to 4. So we can simply draw our circle by going 4 units in each direction from the center of our circle and drawing a smooth curve through those points, like so. So you can see drawing a circle is fairly straightforward. Sometimes we might need to complete the square in order to get it in standard form equation for circle. So let's go ahead and jump straight into the ellipse. Now we can see the equation of an ellipse looks very similar to the equation of a circle. We have our x minus h squared, our y minus k squared, where the center of our ellipse is being represented by the point hk. One thing to notice is an equation for ellipse is always equal to 1. Okay, and notice we're seeing two horizontal vertical stretches underneath our perfect square trinomial for our x and our perfect square trinomial for our y. Well, the a and the b are, somewhat, it's unimportant which is which. What is important is their value. So I'm going to label a as being, the value a is going to be half of what we're going to call the major axis, and then value b is going to be half of what we're going to call the minor axis. And we'll talk a little bit more about that in a second. But if we draw an ellipse is somewhat oval shaped with a center and 2 points called foci, or the singular focus. Okay, so those 2 points are called the foci. Now, the definition of an ellipse, okay, as you see here, is a set of all points where the distance of a point from each foci, the sum of the distances from each foci, remains constant. So if I choose this point right here, the distance it is from this foci plus the distance it is from this foci is the exact same as if I were to choose a point over here and add up the distance to this foci and this foci. Okay? So where the values a and b come into play. So if a is the bigger value, or if the value underneath the x minus h squared trinomial is bigger, you're going to have a horizontal ellipse. Whereas if the value underneath the y minus k squared trinomial is bigger, we're going to have a vertical ellipse. So if I draw a quick little bad sketch of a horizontal ellipse versus a vertical ellipse and put the center and a couple foci in there for each one, you can see that the foci in the center all lie along the major axis. Okay, so let's go ahead in our main drawing and draw a major axis and a minor axis. Now this value, according to our little picture here in our definition, the length of half the major axis is what we're calling A, and half the minor axis is what we're calling B. A quick side note, the endpoints of the major axis are called vertices, and the endpoints of the minor axis are called co-vertices. Make special note of, if this was a vertical ellipse, then the vertices would be on the vertical axis and the co-vertices would be on the horizontal axis. Okay, now in defining ellipse, we're going to need an equation, and this equation is going to look very familiar to another equation when we're finished. But what we have to do is we have to define how far away all of our points are. So if we just look at this point right here, this vertex right here on the end. The distance it is away from this foci is this little segment right here. And the distance it is away from this foci is this segment right here plus the value a. So the distance that this point is away from both vertices, the sum of the distances away from that vertices, are a plus this piece and this piece. Well, if you look at the picture of an ellipse, knowing that the center is the center of an ellipse and both foci are equidistant from the center, we notice that this distance right here is the exact same as this distance right here, meaning that this point, the distance away from the center, is the same as this point away from the center, these two foci. So we can say that the distance that any point is away from a foci is 2a. Now, that alone does not tell us very much, but since all points are the same exact sum of the distances away from 2 points of the foci, we can now move our focus to this co-vertice at the top here. And if we draw these distances that this point is from each foci, we notice that we make a right triangle. And when we make a right triangle, we're afforded different luxuries like using the use of SOHCAHTOA, which we're not going to use here. But we're also afforded the use of the Pythagorean theorem. And if I call this value, not C. If I call this the hypotenuse, and this the hypotenuse, knowing that since these two foci are equidistant from the center, that means these two foci are equidistant from this co-vertice, which is on the same minor axis as the center, I know that both of these values are equal to a. Since the sum of the distances away from the foci is 2a, and since these two are the same, each one has to be a. Therefore, we can now solve for the distance from the center to the foci. We can call it c, and use the Pythagorean theorem to see that b squared plus c squared is equal to a squared, or when solving for c squared is equal to a squared minus b squared. Looks very similar to the Pythagorean theorem, but is slightly different because of the minus sign. But it makes sense when you review the proof. So let's jump over and let's do some examples here. So if we look right away at this example here, we see different horizontal vertical stretches. So we're looking at it, we're going, okay, this is standard form equation of an ellipse. The center is shifted right 2, down 1. It's a horizontal ellipse because the bigger number is underneath my x. So I know the length of my major axis, a squared, is equal to 25. So a is equal to 5. So half my major axis is going to be right 5, left 5. And my minor axis is going to be vertical in this case. It's going to be up 3, down 3. And I can draw my ellipse. Now, I don't know where my foci are, and the example's not asking me to find the foci. I'm going to go ahead and find it and expect that we can find it every time, because we know that c squared is equal to a squared minus b squared. We already know a squared, 25, and b squared is 9, so c squared is equal to 16, meaning c is equal to 4, plus or minus 4. So our focus is right 4 and left 4. Our focus will always be, on an ellipse, will always be inside of the ellipse. Let's jump ahead to the next example here. I encourage you to pause the video and see if you can do it on your own really fast. But now we can see that this is our a squared, b squared values have switched. It's the same exact example as example 1, but it is now a vertical ellipse, same center, right 2, down 1. Except now our major axis is going to be up 5, down 5. And my minor axis is going to be horizontal. It's going to be right 3, left 3. And because the a value and the b value simply switched, it's really easy to find the same exact foci. They're going to be up 4 and down 4 from the center along the major axis. Okay, so here we have a different one. Now, you look at it and you think, okay, this doesn't look like the standard form equation for an ellipse, but I notice different horizontal vertical stretches. So I know that it is an ellipse. They're both x squared, y squared added together, both horizontal different and vertical different stretches. So I'm going to go ahead and make this thing equal to 1 by dividing everything by 100. And I end up with an equation that is x squared over 4 plus y squared over 25 is equal to 1, showing me that my center is at 0, 0, and it is a vertical ellipse, up 5, down 5, minor axis right 2, left 2, and I've got my nice pretty ellipse drawn. Okay, so let's jump into another example here. Here we see an equation very similar to the one we did on the front, 25x squared plus 4y squared. We get the addition between the x squared and y squared term and different horizontal vertical stretches. So we automatically know we're going to be dealing with an ellipse, but it's not in the standard form equation of an ellipse yet. So in order to get our perfect square trinomials, we're going to have to complete the square. It's the same exact as a circle, but it's going to be one extra step to make it equal to 1. So let's first put our like terms together. Minus 16y plus 141 equals 0. Now, if you recall back to first semester and all of your Algebra 2 training, that in order to complete the square, the easiest we're going to need a leading coefficient of 1. It's not impossible without a leading coefficient of 1, but with a leading coefficient of 1, it is much easier. So we can factor out a 25, add our additive identity, factor out a 4, add our additive identity, and now we're looking at an opportunity to complete the square. B over 2 squared, 6 divided by 2 is 3, squared is 9, negative 4 divided by 2 is negative 2, squared is 4, and we can complete the square within our factor. Now, we're approaching a very common mistake that a lot of people make. A lot of people will be tempted to reach down and say this is a negative 9. This is not a negative 9. This is a 25 times negative 9, which is negative 225. Okay, remember we factored the 25 out of this 150x, which is the term that we are using to complete the square. So the 25 is part of the completing the square. And in order for it to be the additive identity that we're adding, we need to subtract 225. The same thing's going to happen here with our y term. This is not a negative 4. It is a negative 16. And when we move all of our constants over to the other side, we'll see that we have really close to what we started with up here. All we simply need to do is divide everything by 100 because the equation of ellipse is equal to 1, and we end up with x plus 3 quantity squared over 4 plus y minus 2 quantity squared over 25 is equal to 1. And now it's rinse and repeat. The center of our ellipse is left 3, up 2. It's a vertical ellipse. The largest number is underneath the y squared trinomial. So it's going to be up 5 for half our major axis, down 5, and right 2, left 2 for our minor axis. Finding our foci, we know our foci are going to lie along our major axis. C squared is equal to 25 minus 4, which makes C equal to the square root of 21, plus or minus. Now, the square root of 21 may be hard for someone without a calculator, but if you use a little common sense, you know that the square root of 21 is both bigger than the square root of 16 and smaller than the square root of 25. So it is somewhere between 4 and 5 away from our center. We know our foci lie at negative 2, 2 plus radical 21, and negative 2, 2 minus radical 21, respectively. So we can jump back in. I would encourage you to try the next problem on your own. Pause the video and turn it back on once you've completed it to see if you got the right answer. But it's the same exact process. We're going to factor out our 25 from our x terms, add our additive identity. Same thing for our y terms, factoring out a 9. Add our additive identity. Complete the square. Negative 4 divided by 2 is negative 2, squared is 4. Negative 6 divided by 2 is negative 3, squared is 9. We factor our first 3 terms, remembering that our 25 is now distributed to the negative 4, gives us minus 100. We factor our first 3 terms. We're always going to get a perfect square trinomial. That's hence the reason why we are completing the square. Remembering that our 9 times negative 9 is negative 81. when we add all of our constant terms over to the other side, we get 225, dividing both sides by 225 because the equation of an ellipse must always be equal to 1. We learn that our new equation is now x minus 2 quantity squared over 9 plus y minus 3 quantity squared over 25 is equal to 1. We now have another vertical ellipse. Our center is right 2 up 3. With our half our major axis going up 5. 1, 2, 3, 4, 5. Down 5. Half our minor axis is going right 3. Left 3. We can draw our ellipse. And it looks beautiful. Yeah, the equation is also asking us to find our vertices, our co-vertices. We already found that. And our foci are not hard to find. The distance from the center to the foci squared is equal to a squared minus b squared, which is going to be 25 minus 9. So c is equal to plus or minus 4. I'm going to go up 4. Down 4. And see that our foci, I'll write the point off to the side here, is 2. 3 plus 4 is 7. And this foci down here is going to also have the same x-coordinate, 2. 3 minus 4 is negative 1. The last example here, we're trying to find the equation of an ellipse in standard form. So again, we're trying to make our equation in standard form just like an ellipse that has a foci of 0, negative 2, and 0, 2, and a minor axis of length 6. Okay, well, if we sketch this really quick, 0, negative 2, and 0, 2. If I know the foci are there, that means my ellipse is vertical. My center is directly halfway between there. My center is at 0, 0. I've already got half my equation. Now I know my minor axis is length 6. So my minor axis is going to be flowing horizontal. If it's length 6, it's 3 in each direction. Meaning, since my minor axis is horizontal, it's going to be underneath my x perfect square. So 3 squared, 9. Because my foci are 2 units away from the center, I know c is equal to 2. So because c squared is equal to a squared minus b squared, I know that 2 squared is equal to a squared minus 9. A is equal to plus or minus radical 13, meaning that a squared is 13. I want to finish my drawing real quick and finish out my major axis, which is vertical. Square root of 13 is bigger than the square root of 9, smaller than the square root of 16, so somewhere between 3 and 4. Call it right there. There's negative 3, negative 4 right there. And now I can draw my vertical ellipse. Thank you so much for watching. If you have any questions, bring them to class, and look forward to working with you.